View of section 2.9 mixture problems. So if you turn to page 83, you stop your video if you have to till you do that. Basically, mixture problems are story problems. They have differing values that you have to combine to form one whole. Mixture problems are best solved by using a chart. If you look on page 83, there's a table A. It kind of gives you some ideas of where or what you might put in the chart. I'm just going to do a couple of the problems for you. So just to give you an idea of what that chart might be or what that chart might look like, okay? So let's just start with table B on page 83. If you read the verbiage there, and I'm not going to write the verbiage out, I'm just going to read it to you. I'm sorry, my book turned over. It says, for example, it says if you have peanuts, all right, peanuts that are $3, $3 per pound, and you have cashews that are $7 per pound, okay? And let's say we wanted to make a mixture. We want to mix up peanuts and cashews, but we don't know how much to sell the mixture for. And let's say in this mix, we want to use 8 pounds of the peanuts, and we want to mix 2 pounds of the cashews, all right, which is going to give us a total of 10 pounds of this nut mix, right? And so what if we wanted to know how much we should charge for this mix? All right, how much we should charge for this mix. So we're going to use a chart or a table. All right, usually in the table, the first thing, a lot of times you're going to do the items. So the item, it says we have the peanuts. I'm just going to write P for peanuts. And we have the C for cashews. And then we have the mix, okay? And so in here, we might put the quantity of each one. So in this one, we said what? They wanted, in the mix, they wanted 8 pounds of the peanuts. They wanted 2 pounds of the cashews so that they got a mix of 10 pounds. Then we have the unit price. Okay, how much is it, the unit price per pound? Well, they told us that the peanuts was $3, right? They told us this was $7. Okay. And then your last one is always going to be a total. When I said that you're going to be making it a whole, this is going to be the total cost. So if I needed to know what was the total cost, well, the total cost, if it have 8 pounds at $3 per pound, then that would be 8 times 3, right? And here, if we had 2 pounds at $7 per pound, that would be 2 times 7. That gives us the total. Right? And so we could figure out the total here. If we wanted, we could go ahead and say make this 24, make this 14. Okay? And this is going to give me 38. That's one way. So now we know that the total cost for these is 38, but I wanted 10 pounds. And if I want to know how much is it per pound, all right, then this is the unknown. How much is it per pound? That's the unknown that we have, all right? Another way, instead of writing 14 and 24, what a lot of times that you'll see is I'm taking the total, and I wanted you to see that I was summing that up. So really, this total cost would be 8 times 3 plus 2 times 7. right? I'm taking the total, but this is how I represent it. So remember, this is the amount of pounds, and this is the cost per unit, and I want to find out what the cost is per unit. So it's in this place that I'm going to put a variable. And I know if I take the quantity times the unit price, which is 10x, it should equal what this total cost is. And I'm going to go ahead and write it this way, just so that you can see the math. So the 10x, and then I'm going to write that there. All right, and of course the 10x, as you knew earlier, this is 24 plus 14. And remember, we'd gotten 38. All right. And I'm trying to find, I'm solving for x. I'm going to divide both sides by 10. Okay, when you divide by 10, that just ends up moving your decimal over one place. And so what we now have, remember, this, what is the 3.8 representing? Is it representing the quantity? Is it representing the price? It's representing the price. So this is, we're talking about money here. So basically that means we would charge $3.80, because we're talking about money. You wouldn't say 3.8 per pound of the mix. So once we mixed it, we would be charging $3.80. $3.80 per the mix. But mixture problems involve, like I said, the table. Let's look at another example. Let's look at page 85. I'm going to do example 2.9b. And again, go ahead and look at your book, because I don't want to write out the story problem and read it. You can pause the video if you need to. It's tickets to the West Side Christian School Science Fair were $4 for an adult. So the adults, they were charging $4 per ticket. Okay, because we're talking about tickets to the science fair. And they were charging, for students, they were charging $2. Okay, they said if, right, 850 tickets were sold and they collected $2,620. The question is asking how many adult tickets did they sell and how many student tickets did they sell. Okay, that's basically what the question is asking. So we're going to do our chart. All right, remember this first one is the items. So what are the items that we're talking about? Well, we're talking about the adult tickets and the student tickets, right? That first next quantity is the quantity. Next one is the unit price. And the last one, remember, is the total cost. Okay. So let's fill in what we know, right? We know the unit price of adult tickets is $4, so we're going to put it here. We know the student ticket is $2, so we're going to put it here. Now they tell us that we sold what? 850, sorry, I put it in the wrong place. 850 is quantity. Okay, so they sold 850 tickets and they collected $2,620. Right? So what we do, we need to represent some unknowns here with some variables. So if I said X represents how many adult tickets we have, then you got to think, how can I represent how many student tickets by using that same variable X? Well, if a total of 850 was sold, if I take 850 and I subtract how many adult tickets we have, what remains is the number of student tickets. So this expression can represent how many student tickets were sold. And then going across here, we know that the total cost would be represented by $4 times the number of tickets, $2 times the number of tickets. All right. And then we get here, we know that if we take these two and we take the sum, it's going to represent the total here. So that's where you begin to write your equation. So you're going to take 4x plus this, the number, cost of the student tickets, and set it equal to $2,620. Now we have a math equation with one unknown, and we're going to now solve. So this is 4x plus, I'm going to take 2 times 850, which is 1,700, and 2 times a negative x, which is a negative 2x. Simplify 4x minus 2x gives me 2x plus the 1,700. Remember, you can only combine like terms, right? Now we're ready to go ahead and do the opposite operation so that we can get x by itself. That's our goal. We're trying to find out what x is. This is 0. 2x plus 0 is 2x. And then 2,620 minus 1,700 is 920 when you do the math. We still don't have x by itself, so we're going to divide both sides by 2, and we end up with x equals 460. Now, think about this. Is this what was x representing? Is this money, $460? Is this 460 tickets? What is this? Come back up and look at your chart. X represented the quantity. And so x represented how many adult tickets we sold. So you would say we sold, or they sold, 460 adult tickets. And now we need to find out how many student tickets they sold. Student tickets. Well, we got to go back up here to our original thing. We said 850 minus x represented the number of student tickets. So we have to take 850. Remember, we're going to plug in 460 in for x. 850 minus 460. When you do that, you end up with, excuse me, 390. So that means there's 390 student tickets. So we were able to find out how many adult tickets were sold and how many student tickets were sold. I'm hoping y'all could see that. How many adult tickets were sold, how many student tickets were sold. So that's another example. Let's try one more. Let's go to, I'm taking a little longer because sometimes these are a little more challenging. Let's look at page, let's do 2.9a. This is on page 84, and you can go ahead and look at some of these other examples. So, but I'm going to go ahead and do one more for you, and there are some other examples in the book that you can study. But it says Marcy Perch has 33 dimes, and nickels, with a total value, so the total value was $2.50. How many of each coins does she have? So basically, how many nickels and how many dimes? How many of each coin does she have? That's the question. So again, we're going to make our chart. So I hope you're seeing a pattern here. What's the item that goes in the first? Well, we're talking about dimes and we're talking about nickels. So we have dimes and nickels. And then we have quantity. We have the unit price. and we have the total cost. So I hope you're seeing a pattern here. All right, well, how much is 1 dime? 1 dime is 10 cents. Remember, unit means one price, 10 cents. How much is a nickel? A nickel is 5 cents, right? Now the question is asking us how many of each do they have. We know that there's a total, right, of 33. She has a total of 33. If we were to add how many dimes and nickels, it would be 33 coins. So we know there's a total of 33 coins. We know that. We also know that the total value of those 33 coins is $2.50. So again, we've got to plug in a value here in order to fill these in. So I'm just going to say, D. Let D represent the number of dimes. And if there's a total of 33, if I take 33 minus D, that difference will tell me how many nickels. So this expression can represent the nickels. So if I have D number of dimes times 10 cents, that will tell me exactly how much money I have there. Same thing here. If I take the 5 cents and I multiply it times this expression that's representing the number of nickels, makes sense, right? If I have 2 dimes, right, then 2 times 10 is 20. I have 20 cents, right? So you see how that's representing the cost. All right, so what I do know is that this plus this, and you always are going to get something like this. This plus this should equal that total cost. So excuse me. So we have this expression plus this expression equals the total of $2.50. Now we have an equation with one unknown, and we just need to solve. So I'm going to write 0.1010. I'm going to distribute this 0.5 out. Okay. Now, what I could do before I do that, I could go ahead, and I think I'll do that. If you notice, we have decimals. I can get rid of the decimals by multiplying by what? By 100. Because remember, there's 2 numbers behind the decimal, 2 numbers here behind the decimal, and 2 numbers behind the decimal. So I could take this whole thing and multiply it by 100 and get rid of my decimals. So when I do that, that's going to end up making this now 10D. This is going to move over and make this 5. Now some of you are saying, well, why aren't you taking 100 times all this? This is a product. You're taking 100 times each term. Remember, a term is divided by addition and subtraction, right? And then when you take 100 times this, you're going to end up with 250. All right, now let's go ahead and simplify. You take 5 times 33, which is 165, and 5 times the negative d is a negative 5d. 10d minus 5d is 5d, plus your 165. And you just keep solving. I want to subtract 165 from each side. That's 0, so I ended up with 5d equals 250 minus 165 is 85. And then we're going to divide both sides by 5, and that divides into that evenly 17 times. So this tells me that we have, how many dimes do we have? We had 17 dimes, and we need to find out how many nickels. Remember, nickels is 33 minus D. So I need to take 33 minus 17 to find out how many nickels we have. Well, 33 minus 17 is 16. So that means I have 16 nickels. Okay, because that's what that represents. I have 16 nickels. And you can check your work, because how many coins did they tell you that we had originally? 33. Does this add up to 33? Well, by golly, it sure does, doesn't it? So the answer is there's 17 dimes and 16 nickels. So go ahead and look at some of the other examples and see if you can figure them out.